All right, let's jump into this practice exam from fall 2019 for the ME200 final exam. We'll start with question 1, which is a series of multiple choice questions, and it just says fill in the circle for the correct answer for each question. No justifications are needed on any of the questions. So we've seen these kinds of multiple choice problems before in the midterms. As always, we want to move through them as quickly as possible here since we don't need any justifications and we can't get any partial credit for these. So make sure you're doing that while you're practicing, just moving through these as quickly as you can. I'll give some more detailed explanations, but we don't want to spend too much time on the exam if we can help it. So we'll start with part A here, which says a solid piece of copper undergoes a cooling process from state 1 to state 2 with a heat transfer from the copper to the colder surroundings. The change in entropy per unit mass of the copper is 0, negative, positive, or cannot determine. So I've sketched out a copper block here just so we can visualize what's going on. So we're just going to have heat transfer from this block to the surroundings. Like it says, we have heat transfer from the copper to the colder surroundings. So initially, the temperature in the environment is lower than the temperature in the block. And then there's heat transfer out of the block. And so the temperature of the copper here is going to decrease as we have some heat transfer going out of the block. And so we can already see here, just from the problem statement, that T2 of the copper is going to be less than T1. Another way of writing this that's going to be useful later is if we just divide both of these sides by T1, then we see that T2 over T1 is less than 1. And this is useful because here we have a solid piece of copper. And so whenever we see solids, that means that we have an incompressible substance. So this copper is going to be incompressible because we treat all solids as incompressible substances. And we have a section of the equation sheet dedicated to incompressible substances. So let's go down and look at that because we have a direct relationship between changes in entropy and changes in temperature. So down in the equation sheet, in the models section, this last row here is reserved for incompressible substances and also this compressed liquid approximation. But these three equations here we can use for incompressible substances. And mainly this one, we see a direct relationship between changes in entropy and changes in temperature. So from this equation, if we just integrate both of these terms here, this C, this constant specific heat, is a constant, so we can take it outside the integral. And this ds will become a delta S. And then remember, the integral of dt over t is going to be a natural log term. So I'm going to write that integral up near our problem. Right here, this equation just becomes S2 minus S1 is equal to C times the natural log of T2 over T1. Right, the integral here of dt over t from T1 to T2 is just equal to natural log of T2 over T1. So make sure you're comfortable with this integration. But like we just saw, this term T2 over T1 is less than 1, so that means this term here is less than 1. And if we take the natural log of a term that's less than 1, then that whole term becomes negative. So I'm going to write this here. This term is all negative. And this is going to be a positive constant here, this constant specific heat. So we see that this whole left side also becomes negative. So our final answer here is just going to be that S2 minus S1 is a negative. So we're able to get there because we can use our incompressible assumption for any solid block. And we see that there's a heat transfer, so the temperature is decreasing, and we end up with a negative change in entropy as we cool down this copper block.